So last time I stopped here on this slide, right? Discussing different paths of EMR when it travels through atmosphere of the Earth. And today in this video, I'm going to introduce actual methods for atmospheric correction. So the first type of atmospheric correction is called radiative transfer modeling. We're going to use radiative transfer models to quantitatively address the rationale of EMR transmittance in atmosphere. So here is a list of famous radiative transfer model programs. They can be used to address the accurate transmittance process of EMR in atmosphere. So the advantage of them is that they can be used anywhere around the world because they're rationale models. They have nothing to do with statistics. They only care about the actual mechanism of EMR transmittance in atmosphere. That's the advantage. And they are very complex. Of course, that's disadvantage. And another disadvantage is that when you're trying to use them, you have to provide very accurate, very complex atmospheric parameters for the area you are interested in, for the area of the image. Okay, and these parameters, they could change due to different weather, due to the change of seasons. Okay, so they are very complex, but relatively they can be widely applied around the world. Okay, pros and cons. And here is an example of atmospheric correction using ADCORE model here. On the left side is original image of agriculture area because we can see different agriculture lands here. And you can see on the left side, before atmospheric correction, there are clouds. I would not say clouds, say haze around the map, around the image here, right? Here, right here. And in the middle, there is a huge haze across the image from left to right or from west to east, right? Here is another haze. And after the correction, you can say all hazes, they are eliminated. Okay, so it looks like magic, but it's not because the radiative transfer model here is to address the transmitting of EMR in atmosphere if you can provide very accurate, very well measured atmospheric parameters within this area in that season or even on that day. It can efficiently eliminate haze and very light clouds. Okay, and here in this class, I'm not going to go deep with these models, okay, because they're just too complex for this entering level remote sensing class. But you should know this is what they can do. This is what they can do. Okay. So on the other hand, empirical line calibration is relatively straightforward, is relatively say easier, simpler than radiative transfer models. But the disadvantage of empirical models is that they cannot be applied widely around the world. In fact, these empirical models, they are created for a specific area, for a specific season, or even for a specific image. Okay, so once the area is changed, once the season is changed, once once you are looking at another image, you may need to create another empirical model for that scenario. Okay, that's a disadvantage. Okay, so absolute atmospheric correction (ELC) forces the remote sensing image data to match in situ spectral reflectance measurements obtained at approximately the same time and on the same date as the remote sensing overflight. Okay, so you can see here, in order to create these empirical models, one method is to create the statistical relationship between the data collected by by sensors on a satellite or on a plane, and the in situ measurement using a field spectrometer. Okay, okay. And sometimes if you cannot match this very strict requirement, you can do the field measurement on a random day, say a sunny day, and use the data you collected on the ground as a reference for future use, of course, for that specific area or for specific land cover types. Okay, empirical line calibration is based on the equation listed here. So we have different input and parameters here. So BVK is the digital output value for a pixel in band K. So this is BVK is the output of this calibration. So in other words, BVK is the calibrated value for a pixel. So rho lambda is the scaled surface reflectance of the materials at wavelength lambda. So here is rho lambda. It is the original value of a pixel in an image, which means it is value before calibration, before correction. So here the important parameters are AK and BK, because you're going to use AK to multiply the original pixel value and plus this bias BK to get the corrected value, right? So AK is a multiplicative term, or we call it gain, affecting the BV. It should be BVK, right? But BV. BK is an additive term. Sometimes we call it biased or biased term, or simply offset. So I mentioned before that you need to create an empirical relationship between field measurement and your image, right? So here, this is a linear statistical relationship between your what? This is the empirical relationship established for the correction of your image pixels. Okay, so in order to establish this relationship, we need to find AK and BK, right? Because rho lambda is the input, BVK is the output. So in order to do this, of course, you need to have a remote sensing image collected or created by a sensor. On the other hand, you need field measurement as reference. Here is how you do the field measurement. So field crew taking a spectrometer measurement from a calibrated reflectance standard on the tripod. So here you can say this is a handheld, or you can say it's a field spectrometer, right? Here is the detector on this rod, and here is a standard whiteboard. Okay, what does it mean? You can consider a spectrometer as a very accurate remote sensor, but it is not mounted on an airplane or a satellite. It is used for high accuracy field measurement. So why are you detecting the reflectance at different bands of this whiteboard? This whiteboard here is serving as a reference. For example, when we're talking about Celsius degree, it's not very widely used in US, but I think you know that, right? Celsius degree is a measurement of temperature. How do you define 0 Celsius degree? We say that 0 Celsius degree is when the water begins to freeze. So that's how we define a reference for 0 Celsius degree. And here the whiteboard here is serving for the same purpose. You may ask, what is white in your remote sensing image? How to define that? Okay, in terms of reflectance, of course. Okay, here is the reference. You use a very accurate spectrometer to detect the reflectance of this whiteboard at different bands, and you use it as your baseline. Similarly, you can do this for a black object. Okay, and you can also do this for different typical land cover type. For example, grass, tree canopy, tree leaves, or asphalt or concrete, you can do this collecting of a reference reflectance library using this spectrometer, right, in your field work, and use this spectral library as the reference for empirical line calibration. So this is a very small whiteboard. Why do we need a huge white square and a huge black square here on the ground? Because they are for the satellite flying over the area. Okay. You can collect the spectra, reflectance spectrum, of course, for whiteboard, for blackboard. You also want to know their reflectance on the satellite collected by sensor, so you can compare them and create empirical relationship. So you can see here, there is no rationale involved. We do in this whole process. We do not care how EMR travels through atmosphere. We only collected reference spectral library, and we only collect data from a sensor flying over this area, and compare them and try to establish empirical relationships between them and finish the correction. So you can tell the difference here, right? Okay. So here is an example. On the top, here is an image from TM, Landsat Thematic Mapper. Okay, it's for Charleston, South Carolina. Okay, so at bottom left, here is a reflectance spectrum of a pine. Of a pixel. That pixel is occupied by pines, so vegetation. So in this figure, the horizontal axis is the band of Landsat TM sensor. Band 1, band 2, band 3, band 4, band 5, band 7. So 1, 2, 3. These three bands, they are for blue, green, and red. Band 4 is for near infrared. Okay, we only care about the first four bands because it's vegetation. This spectrum is for pine trees. Okay, so of course the horizontal axis here is for the brightness value, or you can consider it as the reflectance of pine trees at different bands of Landsat TM sensor. Okay, there are different things, reflectance and brightness value, but they are positively correlated. So for a very healthy, normal vegetation, what's the most important spectral feature, reflectance spectral feature of it? If you remember, it should have very low reflectance at red band, but pretty high reflectance at near infrared band. But you can say that for this figure, for this chart here, it's not the fact. Although the reflectance at red band is pretty low, the reflectance at near infrared band is not very high. Okay, this is a problem. This is due to the interference of atmosphere. So we want to correct it to reveal the true reflectance spectrum of this vegetation pixel. So on the right side, we have the reflectance spectra of this pixel after ELC, empirical line calibration. So here we can tell, we're pretty sure it's safe to say that we're looking at a pixel occupied by vegetation, because the reflectance at band 3, which is red band of TM, is very low. And suddenly, at band 4, the reflectance is pretty high. So there is only one possibility in terms of the land cover type of this pixel. It is vegetation. We can see this huge steep cliff of reflectance from band 3 to band 4, from red band to near infrared band. So you can see the result here is very obvious. It speaks for itself, right? On the left side, it's a vegetation pixel, but you cannot tell that because this difference between red band and near infrared band is just too small to call it. But on the right side, after the calibration, it's very safe to tell anybody that you are looking at a vegetation pixel due to this very significant obvious spectral feature. Okay, so this is why we need empirical line calibration. It's straightforward, it's simple, you only need empirical relationship. And the disadvantage though is that you can only use them for a specific sensor, for a specific area, for a specific season, or even for a specific image. Okay, it cannot be widely applied around the world. Okay, we have introduced absolute atmospheric correction. Now let's talk about a little bit about relative atmospheric correction. It's called a relative because we don't do rational models. We don't even do empirical models. So what do? We manipulate the histogram of your remote sensing images. So the purpose is to normalize the intensities among different bands within a scene. To normalize the intensities of bands of one date to a standard scene of another date. So it's relative between bands and relative between one image and another standard scene or reference image. Okay, so atmospheric measurements at the time of data acquisition are not required because it's relative. Okay, if you require atmospheric measurements at the time of data acquisition, you're talking about absolute atmospheric correction. So let me show you an example here. Here we have the histograms of six bands of Landsat TM for the same image, for this image, for Charleston. Let's just call it this image Charleston. So what is a histogram? Let's focus on the histogram of band 1 here. So the horizontal axis is the brightness value of that band. The vertical axis here is the frequency, for a specific brightness value. In other words, frequency is the number of pixels in that image who have a specific brightness value. So here we can say the highest frequency happens at a pixel value of 64, which means that 64 is the winner in terms of the number of pixels who have 64 as the brightness value. So horizontal axis, brightness value. Okay, and a vertical axis is simply for frequency of pixels. Okay, so original histogram of 6 bands of Charleston scene. So band 1, 2, 3, 4, I think, yeah, 5, 7. Yeah, 5, 7. Band 5 and band 7. So atmospheric scattering in the visible regions has increased the minimum brightness values in band 1, 2, and 3. And the shorter the wavelength sensed by each band, the greater the offset from a brightness value of 0. What does it mean? It means that 0 value has been drifting in these histograms, especially for visible bands. So here is a chart showing you the band value versus minimum brightness value and maximum brightness value of each band. So you can see here for band 1, 2, 3, and even for 4, the minimum value is not 0. Instead, there's some specific integer above 0. Maximum value is not something we care, or say we care in this relative atmospheric correction. So at band 1, the minimum value is 51, which is incorrect. It should be 0. I'm not saying that there should be there should be pixels with 0 value. I'm not saying that. But since the author of the textbook is using this example, he or she must have confirmed that there should be pixels with value 0 on band 1 in this thing. So instead of being 0, the maximum value is actually 51 on band 1. So there is a drifting of 0 here. And we need to use a relative atmospheric correction method to pull it back, to make 0, 0, because here 0 is not 0, 0 is 51. And you can see this phenomenon is obvious for visible bands, 1, 2, 3, blue, green, and red. In near-infrared band, it's less significant, and it is not happening for other infrared bands. Okay, so how to do that? Here we have results of applying a simple adjustment to the data shown in the last slide. Okay, for band 1, 2, 3, and 4, minimum values are zeros now. Okay. Only first 4 TM bands required adjustment, right? Visible bands and near infrared band. And this method does not correct for atmospheric absorption. It's a simply correction of the drifting of 0, Okay, so this is a single image normalization using histogram adjustment. Okay, so if you compare them, what we did is simply moving the histogram of first 4 bands to the left to make sure that the minimum value is 0. But I have to emphasize again, you have to be sure that some pixels are actually should be 0 in your image. Then you can do this. If the fact is that, okay, there is no pixels with 0 on band 1 or band 2 or band 3 or band 4 in this thing, you should not do this adjustment. Okay. So here, we can also use multiple image normalization using regression to address the similar issue. Okay, multiple date empirical radiometric normalization. That's another name. And in this method, we need to find something called pseudo-invariant ground targets. These targets, they do not change spectrally from image to image. For example, vegetation is a bad choice for these targets because the reflectance spectra of vegetation changes from season to season. In winter, there is no green leaves, so their vegetation's reflectance spectra will change a lot in winter. So what could be the great choice for pseudo-invariant ground targets? For example, a parking lot covered by asphalt. The reflectance spectrum of it does not change through time, through seasons. Or even the surrounding environment changed, its own reflectance spectrum will not change. So again, they are serving as what? Reference, okay? Because the reflectance of them should not change from time to time. Okay, but if there is change, you know there is something wrong with the image, right? So that's why you need this invariant ground targets. They're serving as a reference. So we use regression method, okay? Correlate the pseudo-invariant features present in both things being normalized and the reference thing. Like I said, if in a specific remote sensing image, the reflectance of that parking lot changed. You may say, there must be something wrong. We need to do atmospheric correction for this image because the reflectance of the parking lot is not correct. So how to do this correction? You find the reference thing in which that parking lot has the correct reflectance at different bands. And you, again, just like the empirical method I introduced before, you create the relationship, statistical relationship between the referencing and the actual remote sensing image, the actual thing you're looking at. You use regression method to correct the reflectance of that parking lot. And you do this for the whole image, right? Although you're focusing on this parking lot, but when you do the regression, when you do the correction, you apply this regression, you apply this statistical relationship to all pixels in your image. So you can just do the correction for the whole thing, for the whole image, right? So here is an example. We have 3 regression models here. For this specific one, the horizontal axis is for spot band 2 on this specific day, 1987, April 4th. Okay, and the vertical axis is for the same band, spot band 2, but for another date, 1991, August 10th. So we have several black points here. You can consider each one as a pixel. Why, right? Or you can say a pixel is not accurate for a specific position in the real world, right? For example, this pixel is for parking lot. Another pixel is for a water body. Water body is also relatively stable. Water bodies can be chosen as pseudo invariant target to do the correction. Okay, so there are other targets used here, right? So you can say even for the invariant target for the specific day, for day 1, let's say that the value is not, it's very close to 140, but it's not, right? It's 130 something. But for the second day, for day 2, it's above 140, but it's good enough. It's good enough, right? Right. So we have several targets here, and you can use them to create this linear relationship, empirical relationship. And the R square, the strength of correlation is very strong, is 0.984, is very close to 1. So it means that these targets you have chosen, they're good targets. They did not change a lot in terms of reflectance between these 2 days. There is small change, but yeah, it's okay. You can use this model. You can use this empirical model to do the correction, atmospheric correction, for this specific thing, Okay, I'm not sure which one is reference, but usually horizontal one is a reference, right? So I think this image is used for reference. Another image for day 2 is the image you want to do the correction. Okay, so now you have this empirical relationship, regression model. You can apply this relationship to all pixels for that specific image of day 2 to do the correction. So the input is your original pixel value in the image of day 2, and through this model, you get a corrected value y. Okay, so it's very simple. It's very simple and straightforward. But like I said, empirical model, an empirical model, it cannot be applied to another area or for another image, right? If you're still using this image, spot band 2 on this specific day as a reference image, and you change the image for calibration, then you need to create another empirical relationship and use that empirical relationship to correct another image. okay, cannot be widely applied, even you have an empirical relationship already, okay? So the last part of this lecture, I want to talk a little bit about topographic correction. So there is always slope in real world, right? So topographic slope and aspect may introduce radiometric distortion. For example, the solar light is shining from this direction, right? So we have vegetation on this side of the hill. We also have the same vegetation on the other side of the hill. So you can imagine that even they are the same, land cover type is the same vegetation. The side facing the sun has relatively higher reflectance. The side on the other side, on the other side of the hill, this part of the vegetation is in shadows. So their reflectance is lower, that's for sure, but this is not something we want because they are all vegetation. No matter on the left side or the right side of the hill, they should have the same reflectance at different bands, right? So this is the correction we need to do to make sure that no matter the slope, no matter the topographic scenario of your study area, if it is vegetation, if it is a tree, its reflectance should be the same as other trees in your scene. Okay, so that's the purpose. So an ideal slope aspect correction removes all topographically induced illumination variation so that two objects having the same reflectance properties show the same dn in your image, of course, despite their different orientation to the sun's position. Okay, so on the left side, we have a lot of pixels. Okay, horizontal is illumination. The vertical axis is for band to original value. Okay, you can say, the assumption is that all these pixels, they're representing the same land cover type, say vegetation. Okay, and some of them, obviously, they have lower value here. They have lower values here. Okay, due to the existing of slopes. And on the right side, it is the corrected value. Okay, and you can see that they have similar values. They have similar values on this specific band. Okay. So here is the mathematical rationale of the correction. So here is the formula. You don't have to memorize it, but at least you need to understand it. So LH is the radiance for a horizontal surface. So it is the corrected value. LT is the radiance over sloped terrain. So this is the pixel value before correction. So it's about geometry. It's about geometry. So we need theta 0, sun's zenith angle. So the sun is right here. Okay, theta, sorry, the sun is right here. The sun is right here. Theta 0 is angle between the sun illumination and your sensor. Okay, theta 0. And I is sun's incident angle. So I is incident angle. So this dashed line here is based on this specific terrain. It is perpendicular to the terrain, to this slope. So I is the angle between solar irradiance and what? And this vertical line to the terrain. Okay, so as long as you know theta 0 and I value, and of course you know LT is a radiance for a pixel, right? For a pixel representing this slope, then you do this very simple correction for topography, for topography. Okay, for topography. So only models the direct part of the irradiance that illuminates a pixel on the ground. Okay, Okay, because in the real world there could be other light sources, and the solar irradiance is not that simple actually. Okay, shining directly from the sun, because they are scatterings, they are reflecting in the atmosphere. So there could be multiple irradiance from all directions. Okay, they're all shining, they're all illuminating this specific point. So in real world, it's much more complex. So for this specific model, let's just assume this is the situation. Okay, this is the direction of solar irradiance. So it does not take into account diffuse skylight, like I said, scattered skylight, or light reflected from surrounding mountain sides. Okay, it's a very simplified model. So here is just an example, right? So here we have a dark area here and a dark area here, right? Obviously, I think the sun is somewhere here, okay? So that's the reason why there is shadow on the other side of the mountain, shadow on the other side of the mountain. And you need some prior knowledge, we call it prior knowledge, to do this correction, because you need to know that the shadowed area has the same land cover type as the unshadowed area. In this image, I can tell it's a rural area because I cannot say regular squares or urban areas here. Okay, because the landscape here is natural. There is no man-made land cover type here. So it's very mountainous because we can see all those wrinkles. They are mountain edges. Okay, and maybe agriculture area, I'm not sure, because we can say cropland here. I would say cropland or water. I'm not sure because I don't have enough ancillary data to say that. But in general, I can tell this image is for a rural area, and it should be mostly covered by vegetation. That's why it's safe to say that although this area is shaded, is in shadow, and also this area is in shadow, they should be covered by vegetation. So we should do the correction to make sure that the vegetation in this shadowed area has the same reflectance as their counterparts in unshadowed areas. Okay, so after correction, this is the result. Okay, so you can say the shade here, the shadow here has been eliminated. So the vegetation here has normal reflectance as other vegetation around the map. Okay, illuminated by sun directly. And here is the result for the second area, right? Here, originally, this area is this area is shaded because the sun is right here. Okay, but after the correction, this is the result. And you should know that this correction has been applied for the whole image, or you can do it for specific area. It depends on you, right? It depends on you. Okay, so yeah, that's all I want to say about atmospheric correction. Actually, for this lecture is not only for atmospheric correction, it's for radiometric correction, right? And then in next lecture, I'm going to introduce geometric correction. Okay, see you in next lecture. Thank you.